In this video, I want to discuss the actual algorithm for solving towers of Hanoi. So as previously discussed, there is kind of this general notion of how we can move smaller towers and then a larger disk and then a smaller tower again in order to solve the general problem, right? And solve the general puzzle. So the pseudocode that does that is actually here on the right-hand side. So this is the pseudocode for an algorithm that could play a game of towers of Hanoi for an n-sized number of disks. So we have some basic assumptions. First of all, we're going to say that the rods and disks are already modeled with some data structure. We're not going to talk about that, right? This is just pseudocode. And then that's going to be kind of encapsulated by something called move. So there's some bit of functionality out there which encapsulates moving a disk from one particular rod to another one, right? So we're just going to say that's out there. And that'll actually end up being, because that's kind of a basic operation, it'll take a little bit of time, be the thing that we write a growth function for. Okay, so let's take a look at the code on the right-hand side. So we have our towers of Hanoi pseudocode here. So you can see that there are 4 parameters to this bit of pseudocode. So start is basically what rod do we want to start on. Temp is the working one, right? There's three that are available to us, right? So where can we put kind of spare things? And then end, which is the last rod, right? The one there where I want to move everything to it. Final variable there, n, is the tower size, right? How many disks do I want to use? So the first time I call this, right, if I were trying to solve the towers of Hanoi problem, I would say our start is 1, because all the disks initially start there on the left-hand side. They use the middle rod as a kind of a temporary space to move things. And then I'm trying to move them to the end, right, the third most rod. In the example we did by hand, we had 3 disks, so n initially would be 3. So that's how things would start up. Take a look at this program, what exactly is happening. First we have if n equal 1. So this is our kind of our base case, right? What is the simplest possible puzzle I could solve happens to be when I'm moving one disk from one tower to another. In that case, basically it's given that it's going to work for me. So in that case, right, if I have a tower of size 1, only thing I need to do is call move to go from start to end. So I'm moving one final piece. So that's the simplest tower I could possibly move. Don't require any recursion there. Everything is good. Else, right, n is the greater than 1, so it's at least 2, I need to do a little bit more work. So there's 3 steps in here that we had basically talked about when we looked at doing the trace by hand of how exactly we'd move things along. So the first line is going to move n-1 disks from the first tower to the last tower, well, to the temp tower. So the parameters, right? The parameters are set up so the first thing is where you're getting disks from, the last thing is where you're getting disks to. So what this line is saying is take disks from the starting tower, use the end tower as the temporary, and then the temporary as the target, right? So we're moving n-2, right? Meaning, for example, here n-1, meaning here, for example, 2 items, right? From that first tower to the middle tower. All right, that's where we're doing our kind of our first partial decomposition of this tower, right, to move a couple of parts of it. So we do that first thing. All right, and here, right, the way this code is looking, right, is we're moving from start to temp, right? So we're moving from rod 1 to rod 2. Rod 3 is where our end is. We don't want to touch that right now. Second step is to move from start to end, right? After we move that smaller tower, right, the n-1 tower off of that starting rod, that means the only thing left there is the biggest disk. So that biggest disk, I can move it where it finally belongs, right? It belongs on the right-hand side on that peg. So that moves from 1 to 3. All right, this is from 1 to 2. This is from 1 to 3. Then we can go over here and basically say, okay, I need to finish my work, which my work is to go from the middle point, right, the temp, right, which is number 2, over to number 3, right? I have at this point in time, right? So if I jump back to my other slide for a second, right, my initial process is basically to say, okay, I'm going to go from that initial state to the state where I have, the n-1 tower move to the middle, right? That's here. Then I also move that one piece from the first to the very end, and then once I have that, I move the 2 pieces from the middle to the very end, which gets me this over here, right? So those are the 3 things that basically map to these different pieces of code over here, right? We move a smaller tower, move one piece, then move a smaller tower. And at the end of the day, well, hey, we've moved everything from that starting peg to the ending one. So in that case, right, we've moved everything along, and we've at least, solved the puzzle. So now the question is, just how many moves does this particular method make?